In this video, I'd like to bring you to Calc 1 Enlightenment. Now, I use the name here, Calc 1 Nirvana, because in my studies as a high school student of world religions and whatnot, I learned the word nirvana and I didn't have quite the right meaning in mind, but I was close. So here's a definition from vocabulary.com, where nirvana is the beatitude that transcends the cycle of reincarnation, characterized by the extinction of desire, suffering, and individual consciousness. Right? The next thing right here is really what I think of it as nirvana. All my life I thought nirvana is enlightenment, right? That you've reached nirvana, you have complete understanding, you know what's going on. That's the sense that I'm using the word. It has nothing to do with the music group. Now, here we go. Here's Calc 1 Nirvana. If you've got z is a function of x and y are functions of t, then the chain rule that we had in the last video says that dz dt equals the partial of f with respect to x times dxt plus partial of f with respect to y times dy dt. Those f's could be z's or f's, just the way I have this written. Do you feel enlightened? Do you understand all of Calc 1? Well, perhaps not yet. Let me give an example. Here's the deal. I've got y is a function of f and g are functions of x. Okay, so the diagram looks like this. I'm using different letters than up here, but you'll see the reason. So y is a function of f and g are function of x. So that chain rule tells me that the derivative of y with respect to x, right, there's two paths to go through here, is the partial of y with respect to f times df dx, that's this path, and then times the plus the partial of y with respect to g times dg dx, that's that path. Well, for this function, what's the partial of y with respect to f? Well, partial of y with respect to f is 1, right? G is a constant. There's that 1. Likewise, what's the partial of y with respect to g? Well, the partial of y with respect to g is also 1, because f is a constant. And so I get that dy dx is 1 df dx plus 1 dg dx, which I could rewrite as just dy dx is f prime of x plus g prime of x. Imagine that. The derivative of the sum is the sum of the derivatives. Do you feel enlightened? Let's try another example. Here I have y is p of f and g, right? So it's a function of f and g, where the function p is f times g. And f and g I'm thinking of as functions of x. So, same situation as before, y is a function of f and g are functions of x. So y is a function of x, and I can ask for what's the derivative of y with respect to x. Well, chain rule says it's partial of y with respect to f times df dx, plus the partial of y with respect to g times dg dx, those two paths, right? Well, for this function, what is the partial of y with respect to f? Well, you're thinking of g as a constant, so you have g times f. Taking the derivative with respect to f, you get g. There. Likewise, what's the partial of this thing with respect to g? Well, now you're thinking of f as a constant. And the derivative is just f, the partial derivative. And so we have g times df dx plus f times dg dx, which we might rewrite this way as the derivative of f times g is g times the derivative of f plus f times the derivative of g. You ever seen that before? Do you feel enlightened? Let's try another one. How about this one? I'm going to have y equals q of f and g, where the function q is f divided by g. Quotient, perhaps. F and g I'm thinking of as functions of x. So again, y is a function of f and g are functions of x. So y is a function of x because you could plug x in, get both f and g, and then plug those in to get y. And so I can say, what's the derivative of y with respect to x? Well, By the chain rule, it's the partial of y with respect to f times df dx plus the partial of y with respect to g times dg dx, right? Those two paths. Y goes to f and x, and then y goes to g and x. Now, for this function, what is the partial of f? What is the partial of y with respect to f? Well, if you're thinking of g as the constant, this is just f times 1 over g, so the partial derivative is 1 over g. Now we ask what's the partial of y with respect to g? Well, if g is the variable and f is the constant, then I would think of this as f times g to the minus 1, so the derivative would be minus f times g to the minus 2. So there's the minus f, and there's the g to the minus 2. I'm going to get a common denominator here, so multiplying top and bottom here by g. I then have a denominator of g squared. And I end up with g times the derivative of f minus f times the derivative of g, all divided by g squared. Huh. You ever seen that one before? I hope so. Of course not. Do you feel enlightened? Well, let's try another example. This one's a little bit different because now I have y as a function of three variables, f, g, and h, and I'm going to multiply them all together, f times g times h. And f, g, and h, I'm thinking of all of them as functions of x. So the picture is a little bit different, but similar. There's three ways to get from y down to x now. But y is a function of x, and I can say, what's the derivative of y with respect to x? Well, according to a little bit bigger chain rule now, the derivative would be partial of y with respect to f times df dx, the first path. Partial of y with respect to g times dg dx, the second path. Partial of y with respect to h times dh dx, the third path. Well, for this function, what is the partial of y with respect to f? Well, if I'm taking the partial of y with respect to f, I'm thinking of g and h are constants. So this is just f times a constant, and the derivative is just that constant, gh. Likewise, when I take the derivative of this thing, the partial derivative with respect to g, f and h are constants. And so I have just g times a constant, and the constant is the derivative there. And this last one is fg times dh dx, right? Because f times g would be the partial with respect to h, right? H is constant. No, f and g are constants. H is the variable. So you just get fg. And what do we end up with? We end up with that the derivative of a product of three things is the derivative of the first times the other two, plus the derivative of the second times the other two, plus the derivative of the third times the other two. If you think about Calc 1, when you had to do a derivative of a product of three things, you essentially had to do, you put parentheses around two of them, and then you do a product rule and then a product rule within a product rule. And I don't know if you ever got back to looking at the answer and saying, hey, what I had was just take the derivative of each one, leaving the other two alone. So here's the derivative of the first one, leaving those two alone. There's the derivative of the second one, leaving those two alone. The derivative of the third one, leaving those two alone, and add the results. It's that easy. It's that easy. Do you feel enlightened? Maybe. Let's do another example. Here's one. Y equals a function of f and g, where it's just f raised to the g power. And f and g are functions of x. So similar situation to what we've had. Y is a function of two variables. Each of those is a function of one variable. How do you take the derivative of this? Well, what's dy dx? Well, according to the chain rule, it's the partial of y with respect to f times df dx plus the partial of y with respect to g times the g dx, right? Those two paths added together. So for this example, what is the partial derivative of y with respect to f? Well, if f is a variable and g is a constant, this is just like an x to the n power, right? This is just a power rule. So the g comes down and you have f to the g minus 1 power. There it is right there, times df dx. Plus, what's the partial of y with respect to g? Well, now if g is a variable and f is the constant, this looks like an exponential function. And the derivative of an exponential function is that same exponential function times the natural log of the base. So there it is right there, times the g dx. And so this ends up being g of x times f of x raised to the g of x minus 1, parentheses in there, g of x minus 1 power, times f prime of x plus f to the g times the natural log of f times g prime of x. One of my favorite test questions that I give to a calc class after they've learned the rules of differentiation, including logarithmic differentiation, is take the derivative of x to the x power. Now you can do it using logarithmic differentiation, or now you can do it here like this. And I very often have students that do it correct. And then I have some students that just say, oh, x to the x, this is like a power rule. And they do so that the x to the x power, they bring the x up in front and they drop the x 1 by 1. So they'd say x times x to the x minus 1 power. And then I'd have some students say, oh, x to the x, that looks like an exponential function. And so they'll say x to the x times natural log x. Neither one of those answers is correct, but both of them added together is correct. Because when you're combining functions together and then taking a derivative, you do it by assuming one part is constant, take the derivative with respect to the other part, and then switch them and add the results. That is the way it works every time. Every time. Do you feel enlightened? Huh. Let's do one more example. Let's do implicit differentiation. I remember learning implicit differentiation in Calc 1 and getting to the point of really liking it because it seemed like every single one was the same. That is, you start off with an equation with x's and y's all mixed together. You don't have y explicitly as a function of x, right? You have just them all mixed together. But yet, the graph is some curve in the plane, and at each point, there's a unique tangent line, and the slope of that tangent line is what we would want to call the derivative at that point, right? So the question is, how do you find it? How do you, if there is a unique tangent line determined, we should be able to determine the slope. And so that was the process of implicit differentiation. And so what we could do is we could essentially move everything over to one side, leaving just a constant on the other side. If nothing else, that constant could be 0. Move everything over to one side, move it 0. And so you've got this big old function of x and y equals a constant. And we're saying, okay, we're going to take the derivative of both sides with respect to x. And we're thinking of y as a function of x. We just don't know what it is. So this is the situation. You have f as a function of x and y. And x and y are both functions of x. X is a pretty simple function of x. It's just x equals x. Y is a function of x, but we don't know what it is. But we're trying to find its derivative. So we say, all right, here's my equation. Take the derivative of both sides with respect to x. So you're taking the derivative of f with respect to x, and you're taking the derivative of this constant with respect to x. Of course, the derivative of the constant is 0. And so how do you take the derivative of f with respect to x? Well, the chain rule says that it should be the partial of f with respect to x times dx dx plus the partial of f with respect to y times dy dx. That's this right here, and that's still equal to 0. Okay. Well, whatever that is, I'm going to take as partial with respect to x. I'm just going to write that as f sub x. Dx dx is 1, so that's just 1 right there. And then the partial of f with respect to y, I'll just write that as f sub y. And dy dx is, well, it's dy dx, whatever it is. Right? And the thing is, I remember doing this. I remember doing this, saying, you take the partial derivatives. Every time you ran into a y, you had to multiply by, there's a chain rule, so you had to multiply by y prime, or dy dx, however you wrote it. And then you had this big old equation with a bunch of y primes in it, and you moved everything that didn't have a y prime over to one side of the equation, everything that's had it to the other side of the equation, and you factored out the y prime, and you divided, and you got the answer. Every time. Worked the same. It was awesome. Awesome. Now, granted, the derivatives you had to do were a little different each time, but the process was the same each time. But look at this. You got some stuff that doesn't have a dy dx times it, and you got some stuff that does. So the stuff that doesn't have it, move that over to the other side of the equation, and then divide by the stuff that's multiplied by dy dx. Do you feel enlightened? Let's actually do an example of that. I'll leave that on the top here. So here's the equation of, it's an ellipse that's been twisted some in the xy plane, so it's not axes aren't right on the, major and minor axes aren't horizontal and vertical, they're tilted. So, but anyway, I want to find dy dx at any point. So I'll do it by this formula. It says just take the partial derivative of this thing, because I got just a constant over there, everything here. So I got the partial derivative of this with respect to x times -1, and then divide that by the partial with respect to y. Well, the partial with respect to x is 2x plus 2y plus 0. So there's that with a minus sign on the front. And then the partial with respect to y is 0 plus 2x plus 6y, and there that is the denominator. And so the dy dx is that, like that. It's so easy. This is what it would have looked like back in Calc 1. Right? I'd say take the partial derivative of both sides. Okay, so the derivative of x squared is 2x. This is a product because it's 2x times y, and y is a function of x, so I got two functions multiplied together. So it's 2x times the derivative of y plus the derivative of 2x, which is 2 times y. That's the product rule, those two terms from that. And then here I've got a 6y times the derivative of y. Right? Again, we're thinking of y as a function of x here. We weren't thinking independent, right? So when we have a function of two variables, we're usually thinking they're independent variables and one doesn't affect the other. But in Calc 1, this was non-independent. Y was a function of x. And so there was a chain rule here that popped out that dy dx. So I had two y's initially. I have two dy dx's here. Everything that doesn't have a dy dx in it, the the 2x and the 2y, they get moved over to the other side there. The stuff that does stays here, and then we're going to factor out a dy dx to get this thing. And then, of course, you divide by that right there to get this, which I believe is the same thing as what we had up here. Right? One of the things I've learned over the years is that if you've got a type of problem that every single one seems like it's the same, even though it's a little bit different, but the process, it's like there's a bigger picture. There's something else going on behind the scenes. And in Calc 1, all of those derivative rules have something else going on behind the scene. And that something else is the chain rule. And it's right here. Do you feel enlightened?